Voltage drop is a critical concern in electrical systems, especially when powering sensitive equipment like that found in an information technology environment. A voltage drop of 10% is a significant deviation from the intended voltage and exceeds the recommended limit of 3% for branch circuits, as suggested by the National Electrical Code. Exceeding this limit can lead to several problems, including malfunctioning and potential damage to equipment, overheating of conductors, and decreased efficiency and performance. When the voltage supplied to a device is lower than its rated voltage, it may not operate correctly or efficiently. This can manifest as reduced processing speeds, data errors, or even complete failure of the equipment. Overheating of conductors occurs because the same amount of power needs to be delivered at a lower voltage, which means the current must increase. This high current flow causes increased resistive heating in the wires, potentially leading to insulation breakdown and fire hazards. The increased current draw will also decrease the performance and the lifespan of the equipment. The formula used to calculate voltage drop, which is 2 times K times I times D divided by Cm, highlights the key factors that influence voltage drop in a circuit. In this formula, K represents the direct current constant, which is the resistance of 1 circular millifoot of copper conductor. Its value is typically around 12.9 ohms for copper. I is the current in amps flowing through the circuit. D is the one-way distance in feet from the power source to the load. Cm stands for circular mils, which is a unit of area used to express the cross-sectional area of a conductor. Using the numbers provided, with a K of 12.9, a current of 16 amps, a distance of 200 feet, and a circular mil area of 6,530, the calculated voltage drop is indeed 12.64 volts, which corresponds to approximately 10% of a 120-volt system. Given this significant voltage drop, several solutions should be considered to mitigate the problem. Firstly, increasing the wire gauge is a common and effective method to reduce voltage drop. A larger wire gauge has a greater cross-sectional area, which reduces the resistance of the conductor. For example, switching from a 12 American wire gauge conductor to a 10 American wire gauge conductor will significantly decrease the resistance per foot, thereby lowering the voltage drop. The specific wire gauge needed will depend on the load, the distance, and the acceptable voltage drop. To determine the appropriate wire gauge, you can use voltage drop calculators or consult with electrical tables that provide resistance values for different wire sizes. Secondly, running conductors in parallel is another technique to effectively increase the total cross-sectional area of the conductors, thus reducing the overall resistance. When conductors are run in parallel, the current is divided between them, which reduces the current flowing through each individual conductor. This results in lower resistive losses and less voltage drop. However, when using parallel conductors, it is important to ensure that all conductors are of the same material, same length, and properly terminated to ensure equal current sharing. NEC Section 310.10.4 addresses the requirements for running conductors in parallel. Thirdly, reducing the load on each circuit can also help to alleviate voltage drop issues. If possible, try to spread the load across multiple circuits to reduce the current flowing through each individual circuit. This will decrease the voltage drop proportionally. Consider whether some of the networking equipment can be powered from a separate circuit or if the equipment can be reconfigured to draw less power. Fourthly, a voltage regulator can be installed to maintain a consistent voltage at the outlets. A voltage regulator is a device that automatically adjusts the output voltage to compensate for variations in the input voltage or load current. This ensures that the equipment receives a stable and consistent voltage regardless of fluctuations in the supply voltage. Voltage regulators are available in various types and sizes, so it is important to select one that is appropriate for the specific application and load requirements. Some voltage regulators also provide additional features such as surge protection and power conditioning. As a general rule, you should start being concerned about voltage drop when it exceeds the recommended limit of 3%. However, for critical IT equipment, it is often best to minimize voltage drop even further to reduce the risk of equipment failure and ensure optimal performance. Factors that can contribute to excessive voltage drop include long cable runs, high loads, and undersized wires. It is important to carefully consider these factors when designing and installing electrical circuits for sensitive equipment. In this specific scenario, given the 200-foot distance and the potential for varying loads, it is advisable to take proactive steps to mitigate voltage drop. Consider using a larger wire gauge, such as 10 American wire gauge instead of 12 American wire gauge, or running parallel conductors to reduce resistance. Additionally, installing a voltage regulator can provide an extra layer of protection and ensure a stable voltage supply. Always consult with a qualified electrician to ensure compliance with electrical codes and safety standards. An electrician can perform a thorough analysis of the circuit, taking into account the specific load requirements, distance, and other factors to determine the most appropriate solutions for mitigating voltage drop. They can also ensure that all electrical work is performed safely and in accordance with applicable regulations. When selecting a wire gauge, several factors must be considered, including the ampacity of the wire, the allowable voltage drop, and the ambient temperature. The ampacity of a wire is the maximum amount of current that it can safely carry without overheating. The National Electrical Code provides tables that specify the ampacity of different wire gauges based on their insulation type and ambient temperature. It is important to select a wire gauge that has an ampacity that is greater than or equal to the maximum current that will flow through the circuit. The allowable voltage drop is the maximum amount of voltage drop that is acceptable for the circuit. As mentioned earlier, the National Electrical Code recommends a maximum voltage drop of 3% for branch circuits. However, for critical IT equipment, it may be desirable to minimize voltage drop even further. The ambient temperature can also affect the ampacity of a wire. When a wire is installed in a high-temperature environment, its ampacity is reduced. This is because the higher temperature increases the resistance of the wire, which generates more heat. The National Electrical Code provides correction factors that can be used to adjust the ampacity of a wire based on the ambient temperature. When running conductors in parallel, there are several requirements that must be followed to ensure that the conductors share the current equally. Firstly, all conductors must be of the same material. This is because different materials have different resistivities, which would cause the current to flow unevenly. Secondly, all conductors must be of the same length. This is because longer conductors have higher resistances, which would cause them to carry less current. Thirdly, all conductors must be terminated in the same manner. This means that they must be connected to the same terminals or spliced together using the same type of connectors. Using different types of connectors can create differences in resistance, which would cause the current to flow unevenly. The NEC requires that parallel conductors be sized no smaller than 1/0 American wire gauge except under specific conditions outlined in the code. The conductors must also be arranged to ensure equal distribution of current among them. This can be achieved by physically arranging the conductors in close proximity to each other or by using a common termination point. Voltage regulators come in a variety of types, including ferrosonant regulators, electronic tap switching regulators, and solid-state regulators. Ferrosonant regulators are older technology but are known for their ruggedness and ability to handle high surge currents. Electronic tap switching regulators use a transformer with multiple taps and electronic switches to adjust the output voltage. Solid-state regulators use electronic components to regulate the voltage and are known for their fast response time and high efficiency. When selecting a voltage regulator, it is important to consider the input voltage range, the output voltage accuracy, the load current, and the response time. The input voltage range is the range of voltages that the regulator can accept as input. The output voltage accuracy is the degree to which the regulator can maintain a constant output voltage. The load current is the maximum amount of current that the regulator can supply to the load. The response time is the time it takes for the regulator to respond to a change in the input voltage or load current. In addition to these technical considerations, it is also important to consider the cost and reliability of the voltage regulator. Some voltage regulators are more expensive than others, but they may also offer better performance or longer lifespan. Before making any changes to the electrical system, it is essential to consult with a qualified electrician. An electrician can assess the existing wiring, evaluate the load requirements, and recommend the most appropriate solutions for mitigating voltage drop. They can also ensure that all work is performed in accordance with the NEC and local electrical codes. Remember that electrical work can be dangerous, and it is always best to leave it to the professionals. Attempting to perform electrical work without the proper training and experience can result in serious injury or death. NEC Article 210 covers branch circuits, including requirements for voltage drop, conductor sizing, and overcurrent protection. NEC Article 250 covers grounding and bonding, which are essential for electrical safety. NEC Article 300 covers wiring methods, including requirements for conduit, cables, and raceways. NEC Article 310 covers conductors for general wiring, including ampacity tables and correction factors. Always refer to the latest edition of the NEC for the most up-to-date requirements. In addition to addressing voltage drop, it is also important to ensure that the electrical system is properly grounded and bonded. Grounding provides a path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and prevent electrical shock. Bonding connects all of the metal parts of the electrical system together to create a low impedance path for fault current. Proper grounding and bonding are essential for electrical safety and can also help to reduce electromagnetic interference. Surge protection is another important consideration for sensitive IT equipment. Surges are transient overvoltage events that can damage or destroy electronic components. Surge protective devices, or SPDs, can be installed to protect equipment from surges. SPD work by diverting the surge current to ground, preventing it from reaching the equipment. SPD should be installed at the service entrance, at sub-panels, and at individual equipment locations. Power conditioning can also help to improve the reliability of IT equipment. Power conditioners filter out noise and other disturbances from the power supply, providing a clean and stable voltage to the equipment. Power conditioners can also provide voltage regulation and surge protection. In summary, mitigating voltage drop is crucial for ensuring the reliable operation of sensitive IT equipment. By carefully considering the factors that contribute to voltage drop and implementing appropriate solutions, it is possible to minimize the risk of equipment failure and maintain optimal performance. Remember to consult with a qualified electrician to ensure compliance with electrical codes and safety standards. Always prioritize safety when working with electricity and never attempt to perform work that you are not qualified to do. Implementing these solutions can ensure that the networking equipment receives the proper voltage, operates efficiently, and avoids potential damage due to voltage fluctuations. This is particularly important in an IT environment where equipment downtime can have significant consequences. By taking a proactive approach to voltage drop mitigation, it is possible to create a more reliable and robust electrical system for the networking test area.